Welcome everyone to our webinar. We are delighted to have the co-founder of Csoai, Gogo Chen, as our guest speaker today. Welcome, Gogo, and thanks a lot for taking your time to share your insights with us today. Csoai is an expert in the field of speech recognition and AI solutions and has partnered up with TPI Software several times. TPI Software, the host of this webinar, is a software solution provider with 15 years of experience in the financial industry and with a special focus on fintech solutions. Right, for the next 45 minutes, Gogo is covering the basics of speech recognition as well as details regarding latest technologies and developments. Last but not least, you will also gain some insights into speech recognition applications and examples. At the end of this webinar, we will have a Q&A session, so please feel free to shoot out any question you might have by using the chat box in your right-hand corner. We will keep everyone's microphone muted so the speech can go fluently, but feel free to use the chat anytime. We will collect all the questions and answer them after the speech. All right, that's it from my side. Welcome, and Gogo, please go ahead.
All right, thank you very much, Leah, for this fantastic introduction. And I also thank TPI Software very much for hosting everything. TPI Software is actually one of our most important partners in the Southeast Asia market. And it is also a clear leader in that market. It's helping us to get into that specific market. So back to the talk. My name is Gogo Chen, and I'm the co-founder of Csoai. And today I'm going to talk about speech recognition from basics to cutting-edge applications. I'll first talk about what is speech recognition, how people normally tackle these kind of problems, and then I'll talk about the breakthroughs, how people really bring speech recognition to products. And finally, I'll talk about some of those new demos that we've been working on using speech recognition technologies. So let's get started. A little bit about myself. Okay, this is the company. Okay, this is about myself. So I have been working on speech recognition for more than 10 years. I got my PhD from the Johns Hopkins University Center for Language and Speech Processing. I am the co-founder of a set of startups, namely Kit.ai, Csoai, and Bobo.com, all working around the speech recognition and the natural language understanding technologies. I am also the creator of Google's OK Google hardware detection system. So now it is being used widely on millions of Android mobile phones or Google Home devices. And I am also the co-developer of the most popular open source speech recognition toolkit called Keldy. A little bit about Kit.ai. Kit.ai was my first company, started with my partner Xu Chen. It was the CV Insights AI Top 100 company in 2017, and it was acquired by Baidu in 2017. We were mostly working on developer tools for speech recognition and the natural language understanding technologies. And we had more than 100,000 developers at that point over 20 countries. And our investors included Microsoft co-founder Paul Allen's AI2, Amazon Alexa Fund, Majuna Venture Group, and Founders Co-op. And a little bit about this new company, Csoai. Csoai is a Seattle-based startup. It's founded by me and Xu Chen, my partner. Together, we have more than 10 years in speech and language development. And Csoai is targeting on speech recognition and the natural language solutions. And we are partners with TPI Software, Microsoft, Twilio, and so on. This is today's outline. So first of all, I'm going to talk about the task definition. What is speech recognition? And then I'm going to cover the basic techniques for speech recognition. And after that, I'm going to talk about breakthrough, what really made speech recognition work and what enabled speech recognition in products. And afterwards, I'm going to talk about the new trends for speech recognition technologies. And finally, I'll close this talk by talking about the important points to put speech recognition into production and also some of the demos that we've been working on. Okay, so speech recognition. The task for speech recognition is actually pretty simple. So we have the human voice, human speech, and we would like to use machines to transcribe that human voice or human speech into text. And that is the task. So on the left side here, you have the speech signal, and on the right side here, you have the transcripts. And the task is the ASR part, the automatic speech recognition. And we have to use machine learning models to automatically convert that speech signal into transcripts. So that is the task. And what are the classic methods? We'll have to cover a little bit of math, but don't get scared. It's very simple, straightforward math. So remember, on the left side, we have the speech signals, right? And on the right side, we have a sequence of words. So here on the acoustic signal, we are using vector x to donate the acoustic signal. So we have a bunch of vectors, x1, x2, to xn, and that is our input acoustic audio. And we also have this word sequence, word 1, word 2 till word m. And the task is really to find given the acoustic observations or the acoustic signal x, we would like to find the best word sequence that matches this input, right? And we can put that into this probability. So this P, this is the probability of the word sequence given the observation, word sequence W given the observation X. And we would like to find this best word sequence, and that is the task of speech recognition. Now, by applying this Bayes rule, we can actually convert this probability into these two parts. And we normally call them the language model and the acoustic model. So this part is actually pretty straightforward. It is the computing the probability of a sequence of words. It is called the language model, and this part is a little bit more complicated. It is the computing the probability of the acoustic observations X given the word sequence W, and it is called the acoustic models. And we are going to cover briefly on these two parts in this talk. So this is for language models. Remember, for language model, we would like to compute the probability of the sequence of words, right? So suppose we have a sentence here. Sentence is "Where are we going?" And we would like to compute the probability of this sentence. Then what are we going to do? Well, we can use something called the chain rule, right? So the task is to compute the probability of the sentence S. So PS, P of S. So what we are going to do is we are going to decompose this into small parts. So first of all, we have to compute the probability of the first word, where. And after that, we are going to compute the probability of the next word, are, given the word where. And afterwards, we are going to compute the probability of we, given the history where are. And after that, we are going to compute the final probability of the final word going, given the history where are we. So it is kind of like a generation or generating process. So what we are going to do is basically we are actually predicting those words one by one. And to compute this probability of this whole sentence, we can first compute the probability of first word, then the first two, then the first three, and finally the first the whole sentence. And that is what we are going to do. And suppose we have longer words from W1 to Wn, and we are going to do the same decomposition. So we are first going to compute the probability of the first word, then the first two words, then the first three words, and finally the whole sentence. And we can write that into this format. Now, the issue is that when we speak a sentence or an utterance, it can be like arbitrary length, right? It can be a couple of words or it can be very long. So if we have a very, very long sentence, that means computing this term will be very difficult. And what can we do? Well, we can do something called n-gram. It is actually a approximation of this whole sentence. So the idea is that to compute the word I, given the previous history, instead of compute the probability based on the whole history, we can actually only compute the probability based on the previous 1 or 2 or 3 words. So it's kind of like a truncated history. So if we just compute the probability based on 1 previous words, that's 2 words in total, right? And we are going to call that a bigram. And if we are computing based on the previous 2 words, then it is 3 words in total. And we are going to call that trigram. And those are actually the core part of language modeling. So in order to compute the sentence probability of this whole sentence, what we are going to do is we are going to decompose that into smaller parts, and we are basically going to compute what is the probability of a certain words given 1 or 2 or even 3 previous words. So that is the typical n-gram model. And how are we going to how are we going to do that? Well, it's actually very straightforward. We can just do count. So the idea is that suppose we have a bunch of text corpus, and this text corpus has tons of words. And what we are going to do is we are going to count the numbers of the unigram, like 1 word, and the bigrams, 2 words, and the trigrams, like 3 words. We are going to count all those counts. And based on those counts, we can calculate the probability of a certain word given 1 or 2 or 3 hits. And that is what we do for language modeling. Now, remember, we just covered this language modeling part, but we still have this very complicated acoustic model part, right? Acoustic modeling is actually very difficult in speech recognition. The task is to, well, first of all, the task is, given a sequence of words, we have to figure out the probability of a certain acoustic signal. And how are we going to do that? It's actually very difficult. So I'm giving some example here. The first part here, those are all acoustic signal, acoustic features. And those 3 words are all head, for the same word head. Now, when a child speaks the word head, it looks like this. And when a male speaks the word head, it looks like this. And this comes from a female. And these 3 looks very different. So for the same word 0, if the same speaker speaks the word 0, but when the speaker is in a different mode, the acoustic signal can also be different. So this is when the speaker says the word 0 normally. This is when the speaker says the word 0 when he's angry, and this is the soft version, and this is the fast version. Sure, they look somehow similar, but still they are kind of different, right? So how are we going to figure out that? Normally, we use something called the HMM or GMM for that. HMM short for hidden mark models, and the GMM for Gaussian mixture models. So what we are going to do is for each word or each form in this world, we are going to model that form or that word using 1 HMM unit. And for the whole sentence, we are going to concatenate the bunch of HMMs from different words or different forms, and concatenate all those HMMs and get a larger HMM for that sentence. Now, for this HMM, there are 2 very important probabilities. One is this transition probability. So that is the probability jumping from one state to another. And the other is this output probability. That is, at a certain state, what is the probability of generating a certain audio signal or acoustic feature vector? And that's normally how we calculate this probability for acoustic models. Now, putting everything together, for this ASR system, we have 2 very important parts. One is this language modeling, which basically, calculates the probability of a certain words given the history words. And the other is the acoustic modeling, which figures out the probability of the acoustic features or acoustic signal given the sequence of words. And when there's new speech or new audio, we are going to calculate the features for that audio, and we are going to use these 2 models to figure out the best word sequence. So this is the typical speech recognition system. I'm listing here some of this performance over the years. So on the x-axis here, we have the years from 1988 to 2011. And on the y-axis here, we have the word error rate. That is how we measure the performance. And we can look at some of those curves. And you find that the speech recognition is actually very hard. So let's look at this curve. This is for meeting speech. It's like people having a meeting in a meeting room, or maybe even like like us having this kind of video chat, video meeting. And if you look at the performance, you find two things. First of all, over the years from 2003 till 2009, there's really barely any like improvements, right? Or the improvement is very small. The other is the word error rate. If you look at it, it's very high, like 40 or 50, meaning the speech recognition system actually, gets like half words wrong. And you can't really use this kind of system in a meeting transcription system, right? You have like only half of the words correct. So this is not usable. And we can also look at another data set. This is a switchboard, and this is for telephone speech. And I think it is widely used for example, for customer service. It's always telephone speech, right? And initially from 1993, the word error rate is super high, close to 100%, meaning everything's wrong. Then it comes down over the years till 2000. I think it was somewhere around the 20 or 30, high 20s. But then after that, there's literally no improvement. So when you compare that with human transcription, for human transcription, it's typically like a 2% or 4% word error rate, even for like telephone speech, even for very difficult speech, like distant speech, right? But for our speech recognition models, it was in like high 20s or high 30s, or for this, it's even like high 50s, meaning speech recognition systems were actually not very usable at that point. So then there's this breakthrough that makes speech recognition usable. Remember, we have this HMM, GMM model for acoustic modeling, right? We have the HMMs modeling the sequence, and we have the GMMs modeling the emission probability or output probability from the HMM states to acoustic vectors. Now, around 2009, there's this search for neural networks. A lot of researchers are working on neural networks, and they were getting like really promising results on different tasks. And some of those very smart researchers figured, hey, maybe there's something that we could try on speech recognition as well. And this was their first try. So what they did was basically, instead of using GMN, using Gaussian mixture models, they tried neural networks to model this emission probability from HMM states to acoustic vectors. And then they found there was huge improvement. And this was actually just the start. And eventually, they found by using neural networks, they can dramatically improve the speech recognition performance, which really made speech recognition usable. Now, one good thing about this neural network is that we have tons of neural network structures. And we can always try out all those network structures. And I'm sure some of them would perform well, some of them probably won't perform very well. But the key is that we have a lot of model structures we can try. While for the GMM stage, it was just really one very simple GMM model, which was not performing very well. So this is the impact for neural networks on just one task. The task is called TIMIT. It is phone recognition. So again, on the x-axis here, we have the year from 2007 to 2013. And on the y-axis here, we have phone error rate. So instead of having word error rate, since it is a phone recognition task, we have phone error rate. So around 2008, the phone error rate was somewhere around 27%, which was high. Then over the year, I believe this was somewhere when neural network kicked in, and that reduced the phone error rate to 23, and a year later to 20, and 2 years later to somewhere around 17, 18%. So that was, by simply applying neural networks to this specific task, researchers were able to reduce this phone error rate from 27% to 17.7%. And that was a reduction of more than 30%. And by applying all those kinds of neural networks, people really made speech recognition work. So when you look back in the year of like 2011, that was when Apple shipped out the Siri, right? And that was the first time when speech recognition really worked. And I feel neural networks really played a very huge role over there. Now, neural networks made the speech recognition work, but what are the new trends for speech recognition? In my mind, there are two very important trends. The first is end-to-end speech recognition, and the second is pre-training. So for end-to-end speech recognition, the idea is that instead of breaking down speech recognition tasks into language models or acoustic models, we are going to use neural network to model the whole process. So the input to that neural network would be acoustic features or maybe even acoustic signal. And the output of that neural network would be a sequence of words. So that will make the sentence a lot, the task a lot easier. Now for pre-training, we probably know that for a speech recognition task, it is very important to have tons of data, but labeled data is really expensive, and that's why speech recognition is expensive. But if we can make pre-training work, if we can use some unlabeled data for training, and when we go to a new task, we can just apply limited amount of new data to that pre-trained model, then that will save us a lot of money on the labeled data, right? So those are the two most important trends that, in my mind, are very important. Let's get into a little bit of details. So for this end-to-end system, there are a lot of advantages, and some of them are, first of all, we are going to have this simplified system because it is just one neural network, so it is going to be easy to implement. It is also going to be easy to optimize because we only have to optimize the neural networks, and likely it will also lead to less computation because it's just one network. Potentially, we will also get better performance. When you look at this old structure, we have to first, optimize for language model, then we optimize for acoustic model, and then combine them together. But the optimization process may not be optimal because we are not optimizing for the end-to-end results, right? But for this end-to-end system, we are really doing end-to-end optimization. So potentially we can get better performance. And the other is that we can have various neural network architectures, so which will potentially also lead to better performance. So there are two very important sets of models for end-to-end systems. One is called this attention-based encoder-decoder models. So it's one of the sequence-to-sequence modeling. The input and output are sequences with different length, and you have the model in between trying to map this input sequence to the output. So it was first used, I believe, around like 2015 or 16 for neural translation, and it had a huge impact on the task of machine translation. Later on, people started using that for speech recognition as well, and it is so far giving very good results. So for speech recognition, your input would be your speech signal, and you have the model in between, and your output will be your word sequence. The other very important speech recognition end-to-end model is called the recurrent neural network transducer, or RNT. So this is a model proposed by Google around, I believe, 2 years ago, and it's given very good results. Google are using this for mobile devices. So meaning you can run the whole speech recognition just on your mobile phone. By using this model, they were able to reduce the model size from somewhere around like more than 1 gigabytes to somewhere around 80 megabytes. And they got similar results and faster performance. So this is also something that worth a try, and it gives very good results for Google. Now for pre-training, if people from NLP, it's probably a very familiar topic. There's this model called BERT, right? And people probably know from the headlines that models like BERT has been crushing the NLP tasks. The idea is actually very simple. So the BERT key idea is that we have a bunch of data set. We mask out a key percent of the input words, and then we try to predict the masked word. And by setting up this task, we train the model, and we use this trained model for a specific task. And typically that will lead to performance to that specific task. And that will also reduce the data amount that is required for that specific task. And we can apply the very similar idea to speech recognition as well. So this is a typical speech recognition model. We have the input features here. And what we can do is we can mask out a key percent of the acoustic features. And we try to predict the masked features. And we use this pre-trained model as a start model to train a task-specific model. So I'll talk a little bit more on this because this is very important for bringing speech recognition to products. So for products like, for example, customer service, suppose we are having this industry like a bank industry or insurance industry, we are going to have a lot of new terminologies, right? A lot of new words. And most likely we don't have enough data on that kind of industries because customer data, for those industries, customer privacy is really important for them and they won't be able to give away data. So that means for those tasks, you will only have very limited amount of data. But if you can do pre-training, what you can do is basically you can collect a bunch of unlabeled or out of domain data, and you use that data for pre-training. Then you have this pre-trained model, and you can apply your limited amount in domain data, and the performance hopefully will be much better than just using the in domain data. So this will be very important to productization for speech recognition. Okay, so we've covered the task definition, the classic techniques, the breakthrough, the new trends, and now how can we use that, really use that in products? Well, in my mind, there are three very important things to really use that in products. First of all is data. People probably know that data is king for machine learning algorithms. And that is especially true for tasks like speech recognition. So to achieve the state-of-the-art performance, most likely you will have to get this state-of-the-art data. So how can we make that work? Well, first of all, we have a lot of self-collected data for different languages and different tasks. So when a new task comes in, most likely we can find something from this pre-collected data. Now, we also have those tools to create supervised data from like open source data sets. For example, like a YouTube or some other sources like Reddit or things like that. And by using our tools, we can use this, we can create this supervised speech recognition data. And this is going to be way cheaper than ask human beings to label the data. And finally, the pre-training techniques that I just talked about. By using pre-training techniques, we can also greatly reduce the cost for that we would be spending on the data sets. Now, the second part is the optimization. People often say that, for speech recognition, Microsoft is providing APIs, Google is providing APIs, Amazon is providing APIs. So why are you still working on speech recognition, right? But when you think about tasks like for the bank industry or for the insurance industry, the Google or Microsoft or Amazon API probably won't work very well. Most likely because for those industries, they have a lot of terminologies that are specific to their own industry. And for Google or for Amazon or for Microsoft, their general API is not tuned for those new terminologies, those new data. So sure, their API, their speech recognition sort of works, and it works very well on web. But for specific tasks for the bank industry or for the health insurance industry, especially with telephone speech, they may not work well. But what we do is for each of those tasks, we do customization, and we will have one customized model for each of those tasks so that we can guarantee the performance. So here, customization is really the key to the performance. And finally, the on-premise deployment. I briefly talked about it for industries like banks or insurance companies. User privacy or customer privacy is really important, and they want to be able to send the data to a third-party server to do things like a speech recognition or language understanding. They will have to ask you to deploy your whole model to their computers so that everything is handled within their own infrastructure. But this is not possible for example, for Google or for Microsoft or for Amazon. Well, it's at least going to be very difficult for them if it's not impossible. But for us, one of our strengths is really to make everything on premise. So what we can do is we can ship the infrastructure to your network, to your computers, and we can train everything on that specific computer, and we can also serve everything from that specific computer. In that way, you can keep everything within your infrastructure. So that guaranteed this user privacy. So that's how we put everything into production. And till the end, I would like to show you one of the demos that we are working with TPI software. This is for customer service, but for food ordering. So when you think about customer service, typically people would just call someone, right? Call a number and someone pick up the phone and answer your questions. But since some real human beings will have to pick up the phone, most of the time there will be a very long line, especially in this COVID environment. Sometimes the waiting time can be like 1 hour or even longer, which is crazy. Now, what we do here is instead of let a human being to answer your phone calls, we can actually let the AI to answer your phone calls. So by doing speech recognition, we can transcribe your input audio into text. And by doing language understanding, we understand what is your intent and how we should respond to your intent. And in addition to that, instead of just having this phone call, sometimes you can't hear clearly from the phone call, we would also send you a text. So while you are having a phone call, you can also look at the screen on your cell phone and gather all the informations. So that will be a much better experience. And let's look at the demo. I'm sorry. Click on the demo. Oops.
Thank you for calling Taco Bell. I just sent you a link by SMS to enhance your experience with us. You can check out our latest menu via the link. You can also place an order by talking to me or by following the link. According to your calling number, may I please know whether you are Mr. Gago Chen?
Yes, that's me.
Great. I'm setting up your account for you. One moment, please. I have filled in your email address to your account login page. Please enter your password and press the login button. Please let me know if you encounter any problem or when you successfully log in.
I think I logged in.
Welcome back, Gago. Thank you so much for being a loyal customer. I noticed that you ordered bean burrito and crunch tree taco in the past few days. Would you like to try them again, or would you rather to have something else?
No, I think I'm going to have something else since I have a friend joining me.
No worries, Gago. Feel free to check out our menu page. You can ask me to search the menu page or add items for you at any time. Or you can also operate directly on our instant app. I'll be waiting here.
Okay, so I already have some nacho cheese Doritos. Can you show me the combos since I have the friend joining?
Sure, searching for combos.
The chicken looks very good. Can you also show me some drinks?
Okay, searching for drinks.
In the meanwhile, can you check the shopping cart for me?
No problem. Checking shopping cart. One moment. Gago, your cart total is $15.25, and today's order has 1,260 calories.
Oh, that's a lot of calories. You know what? Can you change the Mountain Dew to zero sugar?
Good call, Gago. Replacing the Mountain Dew Baja Blast with Baja Blast Zero Sugar. Done. Update the cart. Gago, your cart total is $15.25, and today's order has 855 calories.
Cool, I think I'm ready to place the order.
Super Gago, your today's total is $15.25 with 855 calories. Shall we use your Visa card ending in 7822 and prepare the pickup at your favorite store at 14506 Boswell Way Northeast?
Sounds good.
Awesome. Please press the place order button. Once pressed, we will ask you to provide your signature. We are all set, Gago. Your order will be ready for pickup in 5 to 7 minutes at 14506 Boswell Way Northeast, Seattle, Washington 98155. Have a wonderful day.
All right, so there was a demo. Couple of things from this demo. First of all, when I talk to this robot, I actually can talk freely. So that puts a lot of stress on the ASR side as well as language processing side. So for the ASR, we really have to handle, for example, accents and sometimes bad audio input. And also, faster speed talkers, a lot of things. So the ASR has to be very extremely accurate to make the NLP side work. Second, instead of just having everything on the phone call, when I had this phone call, our robot actually sent me some messages. And when I click on the message, it showed me this web page so that I can browse all my informations. And that made the whole process a lot more easier. And this is for food ordering, but this can be applied easily to things like bank customer service, for example, or even like insurance sales, right? So when you call some kind of insurance company, and they can immediately send you a message showing you all the possible packages. And in the meanwhile, you can talk to the machine, just like talking to some human beings, right? So this is something that we are working on, and we think this is going to make a much better experience for customer service. And with that, I think I can take questions. That's all I have for today. Back to you, Leah.
Thank you, Gogo. That was really great, very informative. And we also already received quite a bunch of questions. But before we start with the Q&A session, I would like to give everyone a short heads up. So if you are interested in receiving the materials of this webinar today, please scan the QR code or just follow the link in the chat and fill out our feedback form, and then we will be able to send you the materials of today. All right, so let's start with the Q&A. Gogo, I think you received some of the questions already. Which one would you like to answer first?
I think we have 1, 2, 3, 4, a couple of them. I'll try to answer those questions one by one.
Sure.
So, yeah. So first of all, what is the main difficulty in business? That's that's a very good question. So for us, well, speech recognition specific, I think the most difficulty part is about getting the data. So a lot of our customers are banks or insurance companies, and they would like to have this really nice speech recognition system, but they won't give you the data because they can't simply give away customer data, right? But how can you make your system work really well without the customer's data? That was the most difficult part. So we did a lot of things. As I mentioned, we have to collect a lot of well, not necessarily in-domain data for that specific language. And we also create tools to create like supervised data to match that in-domain data. And we also have things like pre-training for making ASR better for that specific task. Yeah, that is very difficult for us, but we are making this work by combining a set of techniques that we are using. So that's the first question. Second one is, what's the current trend for multi-dialect speech recognition? Any workable solutions to employ? For example, how to prepare data and train language models? Multi-dialect. Okay. So this is first of all, multi-dialect is very challenging. We started from ENUS. And ENUS tends to be easier because we don't have a lot of accents in ENUS, right? The most you will have is something like Indian accents or things like that. For that, we basically just dump everything together. We would have like mixed all the data together and train one single model, and it usually performs very well. Sometimes when you go to markets like mainland China or Southeast Asia, things get very complicated, especially like the India market. You will have a lot of dialects and a lot of accents. For that, something you could try is multitask training, right? I have to admit that so far we haven't really tried that. I think the most simple or effective way is still to mix all the data and train one single model. And for one specific task with in-domain data, most likely you are going to make it work. So that's for the second question. The third question is the end-to-end speech recognition already applied on Keldy. How about BERT? So Keldy have sort of this end-to-end, but might be different. So there's one very good model in Keldy called the chain models. It is very like a lightweight and it gives very good performance. So that's something that I would recommend if you want to try it out. But it's very different from the sequence-to-sequence modeling, like the encoder-decoder-based transducer models. It's also very different from the INT models. So in that sense, the transducer models or INT models have not been implemented in Keldy, or at least have not been well tuned. But personally, I really think INT is going to work very well. The technique from Google. The fourth question: are there any fully open source free speech recognition models? Are they any good? It seems like all the best models like Google are pay for use, and that is correct. For all the models, most of the models are pay for use. As far as I know, there are no open source and extremely good models. So there are some open source models. For example, we have been working on a couple of tasks. One was trained on Libre speech. That sort of works. The other was trained on the Aspire data sets. For all those models, you can download from Csoai, but don't expect very good performance from those models. You might be able to make them work by building your own specific language models, but still, it's not as good as, for example, Google service or Amazon service. I think the most important reason was there's no like very large openly available data sets for speech recognition. We are working on something with the universities, but there is still no timeline yet on that. So if that works, we might release some large speech recognition data sets for ENUS, but it's going to take a while. Okay, the next question. Can we build speech recognition services from open source tools? Yeah, I think the short answer is yes, and the longer answer is yes, but it's difficult. So there are tools like Csoai, right? With Csoai, for Csoai, there are like existing scripts with which you can build really good models. But still, it takes a lot of efforts. You have to understand how it works. You have to understand how the scripts work. And you also have to tune the performance. So yeah, I think it is possible, but it's not so cheap, meaning you still have to invest a lot in Csoai. Number 6, what are the most challenging parts when applying speech recognition to products? I think we covered a couple of things on and off. So one thing that we just discussed was the data, right? About how to really get the data. The other parts include, how to do everything on premise, especially for the training or tuning part. How can you train or tune everything on the customer's servers without, giving out all your source code, right? So that's also one of the difficulties. Next question. How about using speech recognition models to create supervised training data? So that's something, the idea is, let me repeat the question. How about using speech recognition models to create a supervised data? So frankly, this is something that people have been trying for a long time. So when you have like unsupervised data, normally what you do is you will create some ASR models from maybe some labeled data, and then you use this model to decode the unlabeled data, and you will have some kind of results, and you can run the iterations over this, and you also refine the decoding process. So so first of all, that is something that people have been trying for quite some time. It works to some extent, meaning you can get something out of this, but it is expensive because you have to run the iterations, and it's also not super accurate. So for companies, sometimes if they do have like enough budget, I think the most straightforward for them is just to send this data to some third-party companies for labeling. Assuming you have enough budget, the better way is to get the sort of like labeled data, but for example, for some audio you may be able to find some kind of transcripts aligned to that audio, but the transcripts may not be perfect. It may not be well aligned. It may have a lot of errors, and it's probably better to work from that kind of data. And you can still find a lot of those data on the web, but it also takes a lot of work to make those data workable or usable for speech recognition. Next question, how about using speech generation models to create supervised data? That's actually a very good question. So we are doing that actually. So what do you do is you can you first can train some speech synthesis models, and then you can use your speech synthesis models to generate some audios, and of course you will have the corresponding text to that audio, and you use that for training. But it only works to some extent, and the part that we found that very useful is like this. Suppose you have like a very specific domain to cover. For example, if your ASR system does not work well for numbers or for addresses, what you can do is you can use this synthesis model to generate audios for numbers or addresses, and you add that data to your ASR training data, and it should improve the whole the performance on that specific domain. The issue is that you can't entirely rely on that data, meaning you still need a lot of high quality labeled supervised data for training. So it only works to some extent, but this is something that we are using. And I believe this is the final question. How long will it take to support a new language or a new domain? This varies from case to case, right? So, for example, for some languages, they are very similar, like in US or most of those Western languages, or some of those like a Japanese language or Chinese language, they are very similar. So it is not too costly to shift from one system to another, assuming you have enough training data. But sometimes, it can be difficult. For example, if you only have the EN-US model and you have to create a Chinese ASR engine out from there, you might have to do a lot of things from scratch. For example, you have to rebuild the dictionaries, you have to retrain the language models, things like that. And that's why, in some sense, end-to-end speech recognition makes things a lot easier. But to put a time on that, maybe if you have enough data and if you already have a very good ASR system on one language, you might need a couple of months or maybe quarters to move from one language to another. And of all this, I think the most important part is really the data. If you can get like high quality supervised data, either by labeling or by created by your tools, that will be the key to speech recognition. So I think that's all the questions. Thank you very much, guys, for having this talk.
Yeah, thanks everyone for joining us today. Thanks, Gorgor. It was really great. And yeah, if you would like to know more about our upcoming events or related articles, please do follow TPI Software on social media or subscribe to our monthly newsletter, and then we will keep you updated. Our next upcoming event will be in December about microservices, so stay tuned and I hope to see everyone there. And don't forget to fill out the feedback form, and then we will share all the materials of today as well. All right.
Cool. All right.
Thank
bye.
you very much. Bye-bye.
Yep.